Welcome, students, to this Masterclass Explainer. Today, we're going to completely demystify the invisible forces that are literally powering your life at this exact second. We'll be taking some complex physics and mapping them straight onto real-world concepts you already know. Trust me, by the end of this session, you'll never look at a wall outlet the exact same way again. Let's get right into it.
Here's our step-by-step roadmap for today. First, we're tackling the flow and the push. Next up, resistance using a super handy pipe analogy, followed by circuit mapping and network architectures. Then, we'll calculate actual power consumption with real-world metrics, and we'll wrap it all up with harnessing heat through energy dissipation. All right, Section 1, the flow and the push, understanding current.
So to really master this stuff, we first have to know what's physically moving inside those wires behind your walls. And we've actually inherited this wild historical paradox. For the longest time, scientists just assumed positive charges were doing the moving, which gives us conventional current. But physics? Well, actual physics relies on negative electrons flowing in the exact opposite direction. Wild, right? Yet, despite that fundamental physical reality, the entire world of engineering still maps conventional current as positive to this day.
Now, you might be wondering, why do these charges move at all? They definitely don't just flow on their own. Our core mental model here is a water tank. Just like a water tank uses gravity to create a pressure difference, forcing water down through the plumbing, a battery expends stored chemical energy to maintain a potential difference. This potential difference, which we measure in volts, acts as the electric pressure that pushes charges right through a circuit. Basically, without the push, there is no flow.
Moving right along to Section 2, resistance, the pipe analogy. As you can probably guess, the pipes carrying this current aren't perfectly clear or completely empty. To grasp how the push and the flow interact, we define Ohm's law. This is the fundamental rule stating that potential difference, the voltage, is directly proportional to the current. In plain English, a harder push creates a faster flow as long as the temperature of the environment stays exactly the same.
So the absolute crucial takeaway is this three-step relationship governing every electrical system out there. Step 1, voltage is the push. Step 2, current is the resulting flow. And Step 3, resistance is the inherent obstacle fighting back against that flow. And we measure that resistance in ohms.
If you're wondering what that resistance actually acts like in the physical world, just picture a pipe narrowing. It's essentially an atomic obstacle course. First, think about the area. A thicker wire allows much easier flow, kind of like a massive waterman. But narrow that pipe, boom, you've got a traffic jam. Length plays a huge role too. The drag is proportional. So if you double the distance the current has to travel, you literally cut the current in half.
Okay, on to Section 3, circuit mapping, network architectures.
Now that we've got our water, pressure, and pipes defined, let's look at how engineers actually architect these plumbing networks in the real world. We really have two main structural options. First, the series network. This is a single continuous path where the voltage splits but the current stays constant. The fatal flaw here, though? Total shutdown. If one single component fails, the entire circuit is dead. Then we have the parallel network. In this setup, the voltage is completely constant across all branches while the current splits up. This is incredibly robust architecture. If one branch fails, it's just an isolated failure. The rest of the system keeps running without a hitch.
To make this super practical, let's think about how these architectures govern your own home. Have you ever had a whole string of decorative fairy lights go completely dark just because of one tiny bad bulb? Yeah, that is the glaring vulnerability of a series circuit. On the flip side, your household wiring relies on parallel circuits. This brilliant design is exactly why you can flick off a light bulb without accidentally shutting down your 400-watt refrigerator or your mechanical fans. They all operate independently. Although, as we'll see in a minute, we absolutely do use series circuits for one very specific safety feature, protective fuses.
Let's hit Section 4, power consumption, real-world metrics.
It's time to transition from the physics of the circuit directly to your wallet. Electric power simply defines the rate of energy dissipation. We calculate it by multiplying the voltage by the current, and we measure the whole thing in watts. Now, this is incredibly important to grasp because, remember, utility companies are not selling you electrons. The electrons are already sitting there in your wires. What they're actually selling you is the energy required to physically push and move them all through your home.
Let's apply this to a real scenario. If we take that 400-watt refrigerator we just talked about and run it for 8 hours, it uses 3,200 watt-hours, or 3.2 kilowatt-hours. This specific metric right here, the kilowatt-hour, is exactly what your utility bill translates into dollars and cents. So when you're looking at your bill at the end of the month, a single unit is simply 3.6 million joules of energy, all neatly packaged into 1 kilowatt-hour. And finally, Section 5. Harnessing heat. Energy dissipation.
So what happens to all that energy once it pushes through the resistance? Well, that brings us to Joule's law, which introduces a fascinating, totally unavoidable reality. Heat produced is proportional to the current squared multiplied by the resistance and the time the circuit is active. Simply put, whenever current faces an obstacle over a period of time, heat is an unavoidable byproduct. You literally cannot have electrical flow through standard conductors without generating thermal energy. This concept acts like a massive energy splitter. Think back to that mechanical fan. Your fan takes the source energy and divides it right into two streams. The first stream is the useful work, spinning the blades to actually cool you down. But the second stream is the unavoidable waste of Joule heating. That's exactly why the motor at the back of your fan feels warm to the touch after it's been running for an hour.
But wait, heat isn't always a bad thing. Engineers are actually absolute masters of harnessing the burn. We designed specific points of extreme resistance just to use this heat to our advantage. Take a classic light bulb. We use a tungsten filament with a massive melting point, pump current through it until it gets so incredibly hot that it emits brilliant light. Or think about a cartridge fuse. We intentionally engineer a weak point. Remember how fuses are always placed in a series circuit? That means if the current ever exceeds safe limits, the engineered heat instantly melts the fuse, physically severs that single path, and protects your entire home from catching fire. Pretty brilliant.
So, let's synthesize our entire masterclass into one complete electrical ecosystem. This is where you see every law and force we've talked about acting simultaneously in a perfectly closed loop. The battery provides the chemical push as voltage. The wire thickness and the components provide the resistance. The current flows based on Ohm's law. And finally, the energy splits, dissipating as both useful light and Joule heating. It's just a perfect, continuous, invisible cycle.
As we wrap up this explainer, I want you to look around the room you're sitting in right now. Really look at it. How many unseen water tanks, complex plumbing networks of pipes, and intricate energy splitters are secretly working together to power your life at this very second? Thank you for joining me for this session, students. I really hope you never take the push and the flow for granted again.